working with. So we've got 2 more days on carbonyl chemistry before we make a complete shift and talk about benzene and aromatic compounds and complicated systems. I just didn't want to push it and have chapter 23 on the exam as well, because I figured that would be a disaster. Not that the exam isn't a disaster already, but it would have been a bigger disaster. So I've got several things to do today. And the first is the Kleisen condensation, which is to esters what the aldol condensation is for ketones and aldehydes. Since it's a reaction of esters rather than a reaction of ketones and aldehydes, you'll recognize that the type of reaction involved is going to be different, right? Because for ketones and aldehydes, we're usually talking about nucleophilic acyl addition reaction. But for esters, which are carboxylic acid derivatives, we're not usually talking about nucleophilic acyl addition. We're talking about nucleophilic acyl substitution. But it shares the commonality with the aldol condensation that we're going to be working with enolate ions as the donor. So it's a new carbon-carbon bond forming reaction. Products are dicarbonyl compounds that have a ketone and an ester, the beta position. So something like that, right? Where the alpha position is the one directly attached to the carbonyl, and then the beta position is ketones. The products are beta keto esters, which is different from the Michael addition, right, where you end up with 1,5 dicarbonyl compounds. In this case, we end up with 1,3 dicarbonyl compounds. So one is a ketone and ester, or we can make it diketones. So it's also possible through Kleisen condensation through a mixed-Claisen to make this kind of compound, a 1,3 diketone. That happens where you have the donor molecule be ketone and the acceptor is an ester. And we'll talk about why that kind of mixed-Claisen condensation is a good reaction when we get into the methods. So the Kleisen condensation, like the aldol condensation, can also occur in a cyclic version. So unlike the aldol condensation, it has a different name. Dr. Diekman had to pay off to get his name associated with the cyclic version of the Kleisen condensation, which is really not a different reaction, but whoever he paid off, it worked. So the cyclic version that creates 1,3-diodes or beta keto esters within a ring is called D3 condensation. The mechanism will be familiar because it's so similar to what you've seen before. But I'm going to show the mechanism with, I think, the same example that the textbook showed with ethyl acetate as the precursor molecule, because that's the simplest molecule we could draw. And I need to actually draw these alpha hydrogens out step is going to be to remove one of those aldehydes. Does anybody remember what the pKa of a hydrogen alpha-2 ester is? Well, first, is it more or less acidic than it would be if it were a ketone?
More.
And to answer that question, we want to apply the usual rule, drawing my resonance structure. Showing that the ester has an additional resonance structure that the ketone doesn't have, where the carbonyl carbon, the positive charge on the carbonyl carbon, is stabilized by donation from the oxygen of the ester, and that should mean more or less acidic. Less acidic, right? So it's going to be less acidic than the ketone because this stabilizes the partial positive charge, which means that carbonyl carbon is not as available to stabilize the negative charge in the alpha carbon. So now the question is how much less acidic. Anybody want to toss a number out there? What is it for a ketone? 15 is an alcohol. Ketone is less acidic than an alcohol.
20? Is it 20-ish?
About 20. 20 to 22 for ketones and aldehydes. For esters, it's about 25. So it's somewhere from 3 to 5 orders of magnitude less acidic. That means that the equilibrium between this molecule and the enolate isn't going to be as favorable. So sometimes the Kleisen condensation takes a little bit more forcing conditions. What base do you think we'd like to use to take that hydrogen off?
It takes more forcing, and I'm guessing it's not hydroxide.
So the key to that question is noticing that if we were to use hydroxide, hydroxide would simply hydrolyze the ester.
Yeah, that's what I was thinking.
So we don't want to hydrolyze the ester. We also don't want to change the ester. And if we used some other base here, rather than the conjugate base that's associated with that ester, we can get transesterification. So by using the same group here and here, we avoid transesterification. Or hydrolysis. And we don't want transesterification or hydrolysis. If ethoxide attacks the carbonyl carbon instead of deprotonating, which is pretty likely because the proton's not that acidic, we're just going to get the ethyl ester back. So it's almost always either ethyl ester or methyl ester because those are cheap and easy to make from the carboxylic acid of ethanol and methanol. Methanol is grain alcohol, methanol is wood alcohol, there's lots of grain and there's lots of wood. So we can make large quantities of ethanol and methanol cheaply. So we're going to use ethoxide, and we're going to take the hydrogen off and form the ester enolate. And that's an equilibrium reaction, but not a very good one. What's the approximate equilibrium constant? You'll see I've drawn it with a very small forward arrow and a very large backward arrow because that equilibrium lies solidly to the left. The other product, of course, is ethanol.
10 to the 10.
So,
Or sorry, 1 times 10 to the 10.
so you're looking at a difference between the
Minus 10.
reactant acid of 25 and the product acid of 15. So that equilibrium constant is on the order of 1 times 10 to the minus 10. That's a pretty shitty equilibrium constant. But the other potential reaction is simply ethanol, or ethoxide rather, attacking the carbonyl carbon and taking out ethoxide again. So that reaction is going to happen a lot, but it's not going to lead anywhere. Right? Even though this is a very unfavorable equilibrium, its reactions actually lead somewhere. Once you have this enolate, then attacking the carbonyl carbon of another molecule makes sense. Because the enolate is quite reactive. So step one here is just deprotonation. That reaction is less favorable than it would be for the ketone, which is what we do in the aldol condensation. But when it happens, then we can move on to the second step. And that's the carbon-carbon bond forming step. But that's not different for the ketone either. We have our nucleophilic attack. So I'm actually drawing this molecule on the left and this one on the right to make the carbon-carbon bond forming reaction more obvious. There's the new bond. Where the alpha carbon of the donor molecule just attacked the carbonyl carbon of the acceptor. Forming a new bond. Step 3 is where it actually differs from the aldol condensation. Because instead of protonating this oxygen, since we have a leaving group, that can come back in and kick out the ethoxide ion. That's a bad leaving group. But we're in base and we already had ethoxide ion to begin with. So it can happen. We don't need those hydrogens. There's no need to draw those out. That is, in fact, the final product that we're looking for in the aldol condensation, but it is not the final, or the Kleisen condensation, but it's not the final step in our base. Because we just kicked out ethoxide ion. And we now have hydrogens that are in between two different carbonyl groups, which means that their pKa is now approximately 11 rather than 25. So this is a very favorable equilibrium for ethoxide to take that hydrogen off and form another enolate. And you really can't stop that. It's much more acidic than the hydrogen you had to take off in the first place. So there's a step 4, which is another enolate formation. And the product of this reaction, of this treating ethyl acetate, in this case with sodium ethoxide and methanol as the solvent, right? The solvent for reactions with alkoxide that's almost always conjugate acid. The product is actually an enolate salt, not the compound. Which direction do we want to push this pair of electrons? Is this pair of electrons going to flow towards the ester or towards the ketone?
Ketone?
Ketone. Why?
I think if it were to go the other way, it would be more likely to push out the other ethoxide ion, and that's not exactly what we want.
There is a resonance, I mean, it's just resonance, it's not going to push anything out.
Oh, okay. Well, I'm thinking almost like the next step.
There is a resonance structure
Okay.
that looks like this. If you were to then push the ethoxide out, you would end up with two cumulative double bonds, a C,
Oh,
C
yeah.
bond, and then a double
Would not
bond.
like
That's
that.
possible. H2C, double bond C, double bond O is called ketene, but it's not as likely. And of course, there's a resonance structure that has a negative charge on the carbon as well. But the major resonance contributor is this one. And the reason is because this carbonyl carbon is already being stabilized by the donation from the ethoxide ion. Since this resonance structure already exists for the ester carbonyl, and when you have this oxygen forming a double bond to carbon, you can't also form a carbon-carbon double bond to it because that would be 5 bonds to carbon. And although some people did that on the exam, it's not really a favorable thing. So it always flows towards the ketone, which makes sense anyway, right? Because things next to a ketone are more acidic than things next to an ester. So it would make sense that the ketone enolate is more readily formed than the ester enolate. So this is the final product. And if we had sodium salt or alkoxide, we have the sodium salt of our ester. What's the equilibrium constant for step 4? I actually should have drawn that with a smaller arrow in the reverse direction because this equilibrium lies
10 to the 4.
It's about 10 to the 4. So this last step is what drives the Kleisen condensation forward, because the first 3 steps are relatively unfavorable in terms of equilibrium. You are decreasing the entropy of the system by creating 1 molecule from 2, so it's entropically an unfavorable reaction, but it's driven forward by a rapid proton transfer at the end, and it shares that in common with saponification, right? Where we drive the 3 not particularly favorable equilibria forward by taking a proton off irreversibly in the last step. This is still reversible, but it favors the formation of ketones.
So we wrote down that the product would be the beta keto ester. So
The product is the beta keto ester, but only after step 2 of the reaction. So if you were to write this reaction out, the reaction looks like this. The 2 molecules of ethyl acetate, step 1, sodium ethoxide methanol, and step 2.
oh, okay. So the acid workup would.
The aqueous acid workup, and this is usually either like 1 molar HCl or saturated ammonium chloride. So without the acid workup step, you don't actually get the beta keto ester as the product. This is a very important molecule in its own right. Ethyl acetoacetate, and it is actually part of another reaction we covered today. The starting material for the acetoacetic ester synthesis. And the acetoacetic ester synthesis is a way to make another ketone. Obviously, it's important when you write this reaction out to distinguish these 2 steps, because you can't mix sodium ethoxide and aqueous acid in the same mixture and get anything other than proton transfer, right? So this has to be over before you do the aqueous acid workup. And you don't want it to be strong acid workup, for reasons we'll talk about a little later. Right? We want a fairly mild acid, we don't want to heat it. So this is usually run at significantly less than boiling temperatures. So step 5, which is protonation, is done in the second part of the reaction. Right? The first 4 steps of the mechanism I have here, and then the last step workup, and it's just the enolate getting protonated by acid. That form the same product that we had at the end of step 3. So you'll be tempted when you're writing this mechanism to just stop at step 3, because after step 3 you've got the product that you were after, but you shouldn't, because you can't stop this proton transfer. The pKa is so much more acidic for the beta keto ester than it is for the ester itself, that reaction is what pushes the reaction forward. So it's a 5-step mechanism, and it shares that with the aldol condensation, right? In the aldol condensation, we had deprotonation in step 1, and then we had a nucleophilic attack. Then we had a protonation of the alkoxide in step 3 instead of leaving, and then we formed a new enolate. We're doing exactly the same thing here. We're forming a new enolate, and then we eliminated hydroxide. So in this case, we formed a new enolate, and then when we did the ester workup, we protonated. So 5-step mechanism, guaranteed you're going to have to reproduce that mechanism at some point, in either this form or the cyclic form, or a crossed-Claisen form, or something. So you should make sure you know that. And on the note card, you should have this reaction that I'm now erasing before you're done with it, where you have the alkoxide base in step 1, and then you have the protonation using either ammonium chloride or dilute HCl. Ammonium chloride is often used as a way of delivering a kind of weaker acid, and you want to make sure that you don't do any acid catalyzed reactions. When we did the Grignard reaction, prior to the dehydration, we used ammonium chloride in the workup rather than HCl, because if you use HCl in the workup, you actually start protonating that alcohol and causing the elimination before the step that's supposed to cause the elimination. And then the other is a bunch of alkene product that you have to separate by chromatography. Using ammonium chloride, which is a weaker acid, we can stop that premature elimination. So, like the aldol condensation, the Kleisen condensation can happen in a mixed or crossed sense. And you'll see both of those terms applied to the Kleisen condensation, where the donor and the acceptor are different. So the question is, what requirements must be met for us to get a good mixed or crossed-Claisen? When are we going to get a good crossed-Claisen, and when are we not going to get a good crossed-Claisen, right? Because if we can have both molecules acting as either a donor or an acceptor, just like in the aldol condensation, there are going to be 4 possible products. And we don't want 4 possible products because, as you learned in lab, separating things is a pain in the ass. Sometimes that's challenging. So when can we get a reaction to go where one molecule is being told, you're the donor, and the other molecule is being told, you're the acceptor? What did we do for the aldol? Because in organic chemistry, you don't want to think of something new until you've exhausted all the possibilities for just using the same shit you already know and applying it to a new situation, right? There aren't that many key concepts in organic chemistry. We just keep applying them over and over to new situations. So what did we do in a crossed aldol or a mixed aldol condensation? And you actually just did one in lab. Most of you. I think everybody has done the aldol condensation by now.
No.
So everyone has actually done an aldol condensation. Got this done. You guys haven't done the aldol yet?
No, that's today.
What the fuck have you been doing all semester?
Thomas's lab, you know?
Ah.
Maybe take that up with her.
No wonder you couldn't do the aldol condensation on this. There wasn't really an aldol condensation. Yeah, there was. It was a second step process. So, we talked about 3 different things in the aldol condensation. that would cause the mixed aldol condensation to be favorable? What were those?
I feel like one was like the aldehyde versus the ketone, like which was the better.
So one was the aldehyde versus the ketone. If you have an aldehyde and a ketone together, which is what you do in the lab that you're doing, the ketone isn't a very good acceptor molecule, right? Because it causes some steric hindrance, so that product is less stable, which means the ketone is usually going to be the donor because everything's equilibrium, and the product of the ketone reacting with itself is less stable than the product of the ketone reacting with the aldehyde. So that's an interesting approach, and it works here. But for a different reason. Because the ketone is 5 orders of magnitude more acidic, if you mix a ketone with an ester, you're going to form the enolate of the ketone much more readily than you form the enolate of the ester. Right? Which means you're going to have a lot of the ketone enolate around and very little of the ester enolate. So since this enolate forms, it's going to react with the ester acceptor molecule before ester enolate forms. And that's just a simple pKa situation. Your ketone is more acidic. Let's use this ketone. So if you take cyclohexanone and you mix it with some kind of ester, you're likely to get a 1,3 ion instead of a beta ketoester, right? Because this methoxide is going to get kicked out. Base, what base do we want to use for this reaction?
Methoxide.
Methoxide, sodium methoxide, because you want to use the same one there. And the solvent, of course, is methanol. So we're going to form the ketone enolate. That's then going to attack itself too, right? It's also going to attack itself because it can, but that product isn't going to be particularly stable. One enolate formation. Nucleophilic attack. 3,
Pick out the leading group.
loss of the leaving groups. So that's the nucleophilic acid substitution reaction, step 2 and step 3 together. That's the product, right? But we're not actually done. What happens next?
The methoxide is going to snag that H.
Methoxide is going to take that hydrogen, push it into the ketone. I have enough room to fit that in here. transfer, but step 5 is the acid workup to generate the product we're after. So when you have a ketone as your donor and an ester as your receptor, the other reaction that ketone would be doing looks like this. The enolating ketone attacks itself. Forms a new CC bond. Looks like that, right? New CC bond here. So step 2, right, after the enolate formation would be still the nucleophilic attack. What's step 3? The aldol condensation. You're not allowed to forget things.
Not what?
You're not allowed to forget things. You still have to know all the reactions from the first exam to the final.
Can you take the oxygen or the negative charge on the oxygen and do an intramolecular, take the H?
Probably not intramolecular. Probably just protonate from methanol.
Okay. Also, random question, but because we have 2 ketones, when we're taking away the hydrogen in the right product that we're talking about, could that hydrogen go either way?
Yes. Wait, what do you mean? Like this hydrogen?
On the bottom, like after step 3, after the leading group goes,
Yeah.
when you take the hydrogen with the methoxide, could it go
Yes, it can
either
go.
way?
It can go both ways.
Okay.
And it actually, this way is pretty favorable because then it puts it next to the benzene ring. But either way, you've got a pi system here and a pi system there and a pi system there, so you've got the pi system extending over all those atoms.
Okay.
And that's favorable. It probably actually goes towards the one on the benzene more favorably because the resonance structure that has a negative charge here and coupled on there is going to be a little bit more stable because it's going to be a conjugated system that's not crossed. So step 3 is always protonate the alkoxide. What would step 4 be if this were the aldol condensation? It's the same as step 4 in the Kleisen condensation. Take the hydrogen off and form another enolate. And the reason I showed the less stable resonance structure over there is so that it would look the same as the resonance structure here that we're showing for the aldol condensation. Right? So this is analogous, except that now instead of having a carbonyl group adjacent to it, we have an atom that has a leaving group. So step 5 is the aldol condensation. Loss of hydroxide. Product will look like this. There's no reason all of that can't happen. Especially since this carbonyl group has a larger partial positive charge on it than the ester carbonyl group. So if you are the ketone enolate and you're looking to attack somebody, yourself is a more appealing choice. But this is significantly less stable than this. That salt of the final product, the salt of the beta diketone, is more stable than this. So this reaction is going to happen, but it's going to keep reversing. Right? Ketone aldol condensations, because they generate this kind of sterically hindered tetrar-substituted double bond, are generally less favorable. And that's why when you have a ketone and an aldehyde together, you typically end up with the ketone as the donor and the aldehyde as the acceptor, because the product of reaction with ketone and aldehyde is more stable than the product of reaction with ketone with acceptor. So all of that's going to happen. The intramolecular aldol condensation, when the ketone attacks itself. It's just that it's not a favorable equilibrium compared to the reaction that generates that nice stable salt. So that's one thing, right? One way to make a cross-Claisen work is to use the ketone as the donor and the ester as the acceptor. And then the product's different. It's not even a ketoester. You'll notice that in this reaction, I also did another thing that makes cross-Claisens work. And I was quiet about it, but I did it. This cross-Claisen would also work.
Is it because they were of similar size? I don't know. Never mind.
No. What's special about that alpha position?
It has no adjacent hydrogen.
There's no alpha hydrogen. So if one of your molecules has no alpha hydrogen, and that's the case in the aldol condensation you're running in lab because you're working with benzaldehyde derivatives, it can only act as the acceptor. And then all you have to do is convince the donor not to react with itself. So how did we handle that problem in the aldol condensation of convincing the donor that it should react with the acceptor and not with itself? You don't even actually have to do that in your reaction in the lab. You're going to mix everything together all at the same time, and because your donor is a ketone and your acceptor is an aldehyde, and the aldehyde is more partial positive charge and less sterically hindered, you're going to end up getting away with it. But normally, since this donor could actually form an enolate, and this carbonyl carbon is no more or less partially positive than the other one, you're going to have to use the trick. Same trick that we use for the aldol condensation. Which is that you take your ester that you want as the acceptor, and then you add the donor molecule slowly. So the order of addition is key, right? You have the base and the acceptor molecule present. No reaction is going to occur between the base and the acceptor molecule other than the unproductive transesterification where the methyl ester generates the methyl ester. And then when you add this, it's more likely to collide with the large quantities of base than it is with the very small quantities of itself. And then it's going to react with the acceptor molecule. So you'll always have a relatively low concentration of this, and a relatively high concentration of the acceptor. And if you can keep the donor in low concentration and the acceptor in high concentration, you can get that reaction to occur favorably. Right? So when the donor molecule has no alpha hydrogen, you can get it, or the acceptor molecule rather has no alpha hydrogen, you can get it crossed-Claisen. So that's number 2. The other time when you can have useful cross-Claisens, or in this case, steaming, is when you do an intramolecular, and you can get one product over the other because of green size differences. Here we have a ketone on one end of the molecule and ester on the other end of the molecule. We have multiple possible products, but one is going to be favored. So what is the product? This reaction. This is where on the quiz. Tuesday. I asked you for the product and to explain why it's the only product. Where would you go with that? First thing I'm going to do is I'm going to draw out the alpha hydrogens. So they're available. I can see them. So those are the 7 hydrogens that could be removed. While you're thinking about that, I'm actually going to stop this video because it's